My name's Dicken, and I'm from Phase Change Material Products Limited, based in the United Kingdom. So today we're going to have a bit of a crash course on thermal energy storage. So what is thermal energy storage? It's the action of trying to store high or low temperature energy to bridge the gap between energy availability and energy use. Now this is very useful with renewables, where the sun doesn't always shine or the wind doesn't always blow. As you can see, little carrots underneath trying to take the cool of the night into the heat of the day, and vice versa. So really we're trying to achieve as much cooling or heating as possible from the natural world and the environment around us. Now, linking to the previous presentation, the concepts of thermal energy storage have been around for millennia. The ancient Persians actually used to use a basic form of ice storage. Well, I say basic, it's basic by today's standards, but it's incredible for the time. So there's a few different types of thermal energy storage available. So one that you might be very familiar with would be your hot water tank at home. So this is sensible heat, which is the heat you can feel. But what we're interested in today is the latent heat, which is the heat in chemical bonds, which we can access, and it's the hidden heat. So think like your ice keeping your drink cold, or something similar to that. So previously, ice thermal energy storage has been used quite a lot, but today we may want to focus on eutectics. So just a quick look at what sensible heat versus latent heat. So sensible heat scales with temperature. However, other things that scale with that are things such as heat losses. Now, using latent heat, we're able to avoid this problem and get around it. So with phase change material, we have quite a wide range, and what you're able to do is almost select this temperature, which allows you to have quite a large amount of energy storage for a very low delta T. So were we to suppose this was, say, 40 degrees, then the temperature difference between 40 and 45, we'd have a much larger change in the energy storage compared to that of sensible heat. So eutectics are mixtures of two or more chemicals, and you're able to change the freezing and melting points. So the main ones that we tend to use are organic compounds, which are things like waxes and paraffins, oils, things such as that. But also we have salt-based solutions, things such as organic salt, glider salts, calcium chloride, and many more. Now, there isn't always a PCM for every single given temperature, and we're always on the lookout for more through our research. But sometimes you have to be able to modify the available PCMs. So just looking at various different types of commercial PCMs, we have temperatures that go down as low as -100 all the way up to 1,200. So just running through the different types, you can have alcohol-based PCMs, so things like your ouzo in the freezer won't freeze. And these are used in backup freezers, but they're not used so often anymore. What we prefer to use is eutectic solutions. We offer a PCM which chills down to -65 and was actually used in incredibly cold shipments, things such as medical shots and things such as that. So more recently, with the Ebola crisis that is in Western Africa, the actual drug is produced in the low countries, and it needs to be shipped all the way to Africa, but under a temperature-controlled environment. Now, our E-65 is the PCM that's actually used in this pack, because they need something that can keep it that cold for that long. Then, most of our applications that we'll speak about today, however, use S-range, which is a hydrated salt. So this is a mixture of salt and water. And this is what we call plus ice. So it's ice that freezes above zero, which is a strange mental concept because ice is inherently cold, and we're so used to that it's hard to detract away from it. Other PCMs which we have are organics, which use waxes, I previously mentioned. High temperatures and metallics, which are often used in more industrial processes and heat recovery, CHP. And then finally, solids. So all of our other PCMs store energy between a liquid and solid. But the X-range uses one solid phase to another solid phase, and there's a latent heat difference between those. So the way that PCM is often presented, especially in all these applications, for industrial applications, HDPE is used, and this is used up to 55 degrees centigrade. These can take many different forms: balls, tubes, stackable containers, things such as that. There's also metal variants of these, which is often much more expensive, which makes the economic case very difficult sometimes. Many of the organics, one of their benefits is that they can take many different forms, things such as pouches, rubbers, granules, things such as this, and these can be used in more niche applications. So actually going into the main area of the talk, and you're all masters of PCM. So what I mentioned earlier is trying to gain as much access to the natural cooling from the environment, for taking the heat of the day into the cool of the night, and the cool of the night to the heat of the day. So our first application is solar innovations. So what we were able to do is use a 27-degree PCM and solar thermal, where a working fluid would flow around, melting the PCM during the day, and then in the night time this provides a radiant underfloor heating. Now this actual installation is in London, and it seems to work even in cloudy places such as the UK, so I've got a lot of hope for many other places. Our second application is in Commonwealth Village in Australia. So they had the intention to try and create a green legacy following the Commonwealth Games, and they wanted to develop a park and a site where they would have houses which would suit a 4-person family. But during the games themselves, there'd be up to about 10 or 11 athletes in a single house, and every single morning they all want a shower at about the same time as well. So by using PCM, we were able to use a 58-degree PCM in a hot water tank in stainless steel balls, where they can build up to this heat charge, which can then be used in one burst, effectively increasing the size of the hot water tank by quite an amount. In the upcoming World Cup stadium, sort of holding to this story of PCMs that be released in a burst. The football stadiums, they're using an absorption collar powered by solar to then charge up the PCM tank for a very long time. This is one of the largest PCM tanks you can get at around 100 meters cubed, offering a significant amount of energy storage. I believe it's 5 megawatt hours, which can then be utilised across a 2-hour football match, which during testing you can see 37 degrees outside and 19 inside, which is perhaps a bit too cold, but maybe they took a hint from the Americans with going very overzealous with cooling. So passive cooling, so trying to take the cool of the night into the heat of the day. There's been much success in countries such as Bahrain and UAE, where you can use tubes installed in the ceilings, and then over the night you can use ventilation to freeze this PCM, and then during the day acts as a sponge for the heat melting. Where this application is perhaps the best is in server rooms, because you can use a higher temperature PCM because computers don't complain, and also your heat loads are a lot more consistent compared to that of an office. You know, some days in an office you might be sick, someone might be visiting, and things such as this. But we can really get around that problem in data centers. So free cooling, I'm sure you're all familiar with the psychrometric chart, but by using a cooling tower, you'd be able to operate this continuously and then store any excess cooling or coolant in a PCM storage tank. So in this case it would be a 15-degree PCM. So a place where this had much success was at the CH2 building in Melbourne, where they used a cooling tower on the very top, and they have a PCM storage tank in the basement. So any leftover cooling after the chilled radiant water beams gets to the very bottom of the building is stored in the PCM tank for later. So during periods of high use, they're able to access this as an extra reserve of thermal energy. So in a heat pump system, you're able to use 2 different PCM temperatures and 2 different types, and then you're able to ensure that no heat or no cooling is wasted, and then you're able to access it at any time. So at a site in Turin, in Italy, they use this example. They use this concept. However, rather than us taking the heat of the day into the cold of night, they actually took the heat of the summer into the cool of the winter. So that we've expanded this concept of the time frame. So inside you can see that these tanks which are sunk to the ground, and this is where these plastic containers are all stacked and stored. So perhaps one of the main applications for phase change materials is in load shifting in AC systems. This allows you to run your system either continuously or to run it in only during favourable periods, such as the night, where you get better COP or often better tariffs. It also allows you sometimes to go from a larger system, actually shift to a smaller, more modest system, but with a large thermal energy storage tank. So just to show this load shifting more graphically, you can see that you can have a peak potentially in the middle of the day when the sun's bearing down, your COP is not very good, your electrical costs are high, and what we're able to do is shift that load and turn it into a flat line, or there's many different load profiles that you could attempt to go after. You could even shut off your system entirely if you really wanted to, but I would really recommend it. So an example of this is Terminal 3 at Bergen Airport in Norway, where they have 100,000 kilowatt hour PCM tanks, which is 4 of our 60 metre cube tanks, once again with stacked phase change materials. And in this example, they run their chillers flat out through the night, where they build up a large reserve of thermal energy that they can access for later. At the Civic Centre in the city of Gosnells, they had a very different problem. So their problem was that they wanted to expand the capacity of their current systems. However, due to bureaucracy and their financial situation, they weren't allowed to increase their AC capacity. They needed to find a way around this. But what they did have was a current system that never ran during the night. So by introducing a phase change material storage tank, they could take this system and run it through the night, effectively increasing their capacity immediately. This tank is effectively built like a swimming pool, which just has the PCM inside of it, so it's not these large metallic tanks, and more just anyone who can build a swimming pool could build one of these tanks. And then our final application, which is once again a little bit different. It's at Parliament House in Canberra in Australia, where they shouldn't have perhaps built a city in this place because it can reach maybe 50 degrees in the summer. It gets incredibly hot and mechanical refrigeration is an absolute must. However, should that mechanical system fail, they have a PCM storage tank backup, which, because of the way that the energy is stored, it's very hard for it to be interrupted. They have a few simple generators which are able to operate the pumps and keep the coolant flowing. So in the worst case, where their HVAC system packs up, they still have a reserve of cool to use. So this tank is very modest, it's only 6 meters cubed, very small, but it gives them enough time, enough cooling for around 2 hours. So at least they can see through the day and have policy done whilst they send the engineers in the night. So some current developments with PCM. So I'm currently working on a passive tile instead of passive tubes in the ceiling. The whole idea of passive is fit and forget, and trying to ensure that a retrofit is as simple as possible, and also allow for some spot cooling by placing them directly above things that have quite a large build-up of heat. So we're aiming to try and reduce heat load by 51%, but obviously this is variable based on the percentage of roof covering and things such as this. Then also, certain PCMs do something called supercooling, which is often seen as a drawback. Supercooling is when something goes below its phase change temperature, yet it's still the wrong phase. So you could have something that's meant to freeze at, say, 50 degrees, except it's sat at 25 and it's still liquid. This would be things that are very similar. Some of you might go golfing and use heat pouches, and they have the little clicker, and that provides a nucleation site, which spontaneously sets it all off. So what you're able to do potentially is use a supercooling PCM, which then stores the energy at room temperature, even though its actual latent heat is at 50 degrees. So it can sit there with very minimal heat losses, and then at the time you need it, you can just trigger it, and then it should be heat on demand. But it's early days, but if we can achieve this, it'd be very good. If you have any further questions that you don't ask today, fire me an email. That's it. Thank you.
Thank you very much.